Dark matter is unlike anything we have ever encountered on Earth. Billions of these strange particles pass through everything they encounter each second. They are so massive in weight, they have the power to influence the galaxies, how they form, and how fast they spin. Dark matter's invisible presence is everywhere, or so it seems. Science has not directly proven dark matter particles exist. There are many suspects, but no answers. And observing something you can't see isn't easy.
It doesn't emit light and it doesn't absorb light. It doesn't interact with light at all.
Not only does it not shine, you can't easily see it in obscuration.
But the evidence is there. Science knows it.
Every textbook on the planet Earth says that the universe is made out of atoms and some subatomic particles. Well, all those textbooks are wrong.
And they are going underground to prove it.
When they hear about this invisible matter called dark matter, they say, bah, humbug, show me proof that dark matter exists.
Sudan, Minnesota. 200 miles from any major city lights. A perfect place for hunting dark matter, but not for obvious reasons.
So you'd think we'd want to look up in the sky for dark matter. That's where dark matter's coming from, after all. But instead, we're going to don our helmets and we're going to walk down into this mine.
2,431 feet underground is the Sudan National Laboratory, an abandoned iron mine reconfigured into a research facility. This is just one lab of many around the world going underground to shield experiments from cosmic rays. Each are racing to detect dark matter, an invisible particle that has only been indirectly observed, but never captured.
We've been at this for now a decade, and we have yet to see a dark matter particle.
The hunt for dark matter started almost a century ago. Astronomers finally had the tools to see deep into the night sky, and the questions began.
So it wasn't until the 1920s that the technology developed well enough so that we could take little fuzzy patches that people had noticed in their telescopes and resolve them and figure out what they are.
Then Edwin Hubble shocked the world and declared the universe was bigger than just the Milky Way.
People realized that some of these little fuzzy patches are separate galaxies, just like our Milky Way galaxy.
As astronomers discovered new galaxies, Caltech professor Fritz Zwicky looked up to the neighboring Coma cluster of galaxies and observed something strange.
When he measured what the motions were in the Coma cluster of galaxies, he got an estimate for how much mass there was in that cluster. Then he compared it to how much mass you could actually see by looking at the galaxies.
Something didn't add up. The galaxies were moving too fast within the cluster for the amount of illuminated stuff he could see. By his calculations, there should have been 160 times more illuminated mass to account for the random speeds of galaxies in the cluster. Something else was affecting their motions. But what was it?
He analyzed their motions and concluded that the cluster could not be stable unless there was a large amount of dark matter present. In 1933, he was one of the first people to really grasp the significance of the presence of dark matter. He called it missing matter.
Dark matter, an invisible mass that was gravitationally attractive and was able to affect the speeds of entire galaxies in a cluster. Revolutionary thinking, yes, but the discovery was largely ignored.
I think that people took Zwicky seriously, but they didn't jump to any conclusions. This was a time when the universe was just beginning to be explored. It was the 1920s when we first realized there were galaxies outside our own. What we didn't know back then was whether it was simply galaxies or stars or gas or dust that we couldn't see, or whether it was something truly different.
Zwicky's observations were based on measuring the mass in the stars and galaxies. But how do you weigh stuff in space?
You can't go and put the sun on a scale. That's a little bit hard. But what you can do is you can measure how fast the planets are moving around the sun. And the more stuff there is in the sun, the faster those planets have to move to stay in their orbits.
Newton and Einstein both said the more mass or stuff you have in an object, the more gravitational pull it will have. And the further an object is from the center, the slower it should travel in orbit, because the gravitational pull is weaker.
According to Einstein's general theory of relativity, or even according to Newtonian gravity, all of the galaxies are pulling on each other.
It's like the sun's influence on our solar system. The mass of the sun pulls Mercury faster than Pluto because Mercury is positioned closer to the sun.
Likewise, for a galaxy, you would expect that you got further and further away, things are moving more and more slowly to stay in their orbits.
But Zwicky didn't observe that. Neither did a young scientist named Vera Rubin 50 years later. She was observing the rotational curves of galaxies similar to the Milky Way. Like Zwicky, her observations also seemed strange.
What Vera Rubin actually measured was that he got further and further away, the velocity of the orbiting gas and dust remained constant.
What Rubin observed was as if a city were a galaxy and every car on the road was a planet or star. And despite the amount of traffic, every car traveled around the city at the same speed. This same consistent rotational speed, despite the amount of stuff or traffic, was exactly what Rubin observed.
The outer parts of the galaxy were rotating fast enough that there must be a lot more mass, otherwise the galaxy would have flown apart.
The only way to resolve this paradox of galaxies which spin 10 times too fast is to assume that there is a halo of invisible matter surrounding the galaxy, keeping the galaxy whole.
Dark matter was present in the galaxies, and it had enough mass to keep the rotation speed constant.
Imagine that I am the dark matter. This ball is a star orbiting me because my gravitational force is keeping it in place. But even if you couldn't see me, you would know that there must be something here, otherwise the star would just zoom off in a straight line. There must be something causing that gravity, and that's how we know that there must be dark matter.
Rubin estimated that there was 10 times more dark matter than ordinary illuminated stuff.
Since then, we've analyzed hundreds of galaxies, and they all have the same pattern. They all rotate too fast for their own good, and they need dark matter to hold them together.
This time, science paid attention and started to wonder, what is dark matter? How do you find something that is invisible in space? They needed to see just where dark matter was hiding out in the universe. And even if they couldn't see it, science realized that dark matter exposed itself by bending light that passes through it. It's called gravitational lensing, and it's a virtual spotlight that uncovers any invisible stuff in the universe.
What it does do is it does what all matter does, and that it can deflect the light ray. So a light ray can be deflected in its path by dark matter.
By tracing the battered light's path, gravitational lensing detected dark matter concentrated in the halos of galaxies. Gravitational lensing proved to be infallible, and dark matter's presence was suddenly revealed.
This technique of gravitational lensing is the most precise because we can actually pinpoint not just how much dark matter there is, but how it's distributed in its position on the sky. And that's because we can measure the distortion of the light rays passing through the dark matter.
How do you know that your glasses are there? Because it bends light. In the same way, by looking at Hubble space pictures of the universe and looking at the distortion of light as it goes through galaxies, we actually have maps of dark matter.
Most of the mass of a galaxy is from the dark matter. The ordinary matter accumulates in the gravitational field of the dark matter.
But once dark matter came on the scene, scientists wondered if it was a new, undetected particle or just invisible, ordinary matter.
When people found dark matter, everybody wanted to know, well, what is it, you know? And of course, the first answer is it's just the stuff that makes up you and me, but it's not shining.
Scientists started to investigate objects in the universe that didn't emit light. Black holes were considered. They don't emit light, can draw matter to themselves, and are detected with gravitational lensing.
It could take the form of black holes or MACHOs, massive compact halo objects, which are basically dark, small stars that don't give off a lot of light.
MACHOs hide out in the halo of the Milky Way and are detected by gravitational lensing. But there weren't enough to account for the amount of dark matter needed. Failed stars like brown dwarfs were also suspected. They are massive enough to make up dark matter's presence. Whatever dark matter is, there is way more of it than the ordinary matter of stars and planets. 10 times more.
All of the stuff that you can construct from ordinary atoms, protons and neutrons and electrons, cannot possibly be enough to account for the total amount of matter that you see in galaxies and clusters.
Scientists continued to present new suspects as the search continued for dark matter. Previously discovered exotic particles like neutrinos were reconsidered. Like dark matter, neutrinos are passing through the Earth millions of particles at a time, but they are too light to account for dark matter's effect on gravity. And scientists can recreate neutrinos in particle colliders. They also come from the sun.
Axions is also another possible dark matter candidate. They were invented to explain a particular glitch in one of the particle physics theories. They would be extremely light, so you search for them in a completely different way than what we're doing. But they would also be very numerous, and so they could possibly be the dark matter.
Axions are very light and are believed to have been created at the moment of the Big Bang, just like dark matter. But theories suggest that they can change to protons, while dark matter is stable. After exhausting all the usual suspects, many scientists believe dark matter is a new exotic particle, unlike anything on Earth. And billions are passing through us every second. Up until the discovery of dark matter, scientists believed the universe was made only of protons, neutrons, and electrons, the stuff everything on Earth is made of.
And we know it has some mass, and we're left with something that we've not yet detected.
But to be a perfect dark matter candidate, it must have certain physical properties, and none of the usual suspects were fitting the crime.
So we know that the dark matter is some ponderous substance. We know that it's not moving too quickly, and we know that we can't see it.
Dark matter particles are not traveling at the speed of light, and they don't interact with you and me or anything pretty well, and that's why it's been so difficult to track down these particles.
And it doesn't interact with ordinary matter except through gravity. If I had some dark matter in my hand, it would have weight, but first it would dissolve right through my fingers.
There aren't any candidates for cold dark matter within what we call the standard model of particle physics.
Like an invisible man passing through walls, dark matter is passing through Earth billions of particles at a time, never colliding with ordinary matter.
So the most popular idea for what the dark matter could be is something called a WIMP.
WIMPs are weakly interacting massive particles. They have not been detected, but their characteristics match the perfect dark matter candidate. At the Sudan laboratory, the Fermilab team has gone underground, braving thousands of bats to try and capture a WIMP particle.
This is called the Cryogenic Dark Matter Search. CDMS is the acronym for it. This was an iron ore mine until 1962 when it shut down. We're half a mile underground.
Fermilab has designed a machine that at sub-zero temperatures can detect a dark matter particle passing through it. And its sensor is made of germanium, a dense metal jam-packed with atoms.
It's a very pure block of germanium. It's got on the surface of it a pattern of tiny little thermometers, basically, that are able to detect when a particle passes through this hockey puck-sized chunk of germanium. Dark matter is streaming right through us right now without doing anything. Very occasionally, it will bump into the nucleus of an atom, and that's the signature that we're hoping to see.
To get a clean dark matter hit, Fermilab needed to filter out junk from space.
We would get so many particles that it would be really trying to sift a needle in a haystack.
Fermilab's experiment picks up all matter that passes through this detector. The less junk in the air, the easier it will be to detect a dark matter particle. Because dark matter doesn't interact easily with regular protons and electrons, Fermilab has frozen the germanium pucks to near sub-zero temperatures.
If a dark matter particle comes through and hits a nucleus, it will actually change the temperature of the crystal very slightly. And so we're looking for that tiny change of temperature in the crystal to signal that a dark matter particle has passed by.
16 germanium pucks sit in a chamber inside a clean room.
So we're suited up, we're about to go into the experimental room. It's a class 10,000 clean room. That's why we're all suited up, so we don't carry in any dust, because that would cause a background for the experiment. So let's go inside. So we have scintillation counters that are catching any cosmic ray particles that get all the way down underground here. So right here is what keeps our experiment cold, that tiny little bit above absolute zero. This is a dilution refrigerator. So way inside here are the germanium and silicon detectors. So we're just waiting for a WIMP, a dark matter particle, to get down to this depth and hit one of those germanium and silicon crystals that's buried way inside all this shield.
Fermilab has been visiting the mine for nearly 2 years, trying to capture dark matter. This is far harder than it sounds. Although billions of particles are passing through Earth at one time, it's a 1 in a million shot dark matter will interact with ordinary matter. Getting a dark matter particle to hit a germanium atom is like an archer trying to hit a bullseye when the target is a mile away.
All of these green lights indicate particles passing through the germanium and silicon detectors that we saw downstairs. These are almost certainly all background particles, but maybe it's buried in there someplace as a WIMP. But we won't know until we analyze the data.
Hunting dark matter is tedious. Each day, the Fermilab team reports to the underground lab, analyzes data, and perfects their ping-pong game while waiting for the one hit that will prove dark matter exists. But for all this effort and waiting around, no dark matter has been detected by Fermilab or by anyone else.
Unfortunately, we've seen precisely 0 dark matter particles so far.
Any day now, we may have the announcement that physicists have captured dark matter in a bottle.
We have a hypothesis. It certainly seems to explain the universe we live in, but the plain fact is we haven't yet detected this cold dark matter particle.
Finding dark matter will not only give us proof of its existence, but might also answer the other big questions of space.
Detecting dark matter directly will give us a window onto what was going on 1/10,000th of a second after the Big Bang.
If scientists can discover what dark matter is, they might also discover how the universe behaved early in its life.
Dark matter is not only a mysterious quantity in the universe, but also it's fundamental to why we're here, in fact. It would be difficult to form galaxies and hence, the solar system and hence life on Earth.
The the story of dark matter and dark energy can't be told without going back to the beginning of time, to the moment of the Big Bang, when space didn't exist.
There is no center where you can point to, and that's exactly the analogy for the Big Bang. There is no direction in the sky from which all the galaxies are expanding.
From this moment of nothing to a violent explosion, space was created, and the universe began to grow from a seed. Particles formed in a nuclear fusion of gas and energy.
Ordinary matter was reacting with other ordinary matter. The early universe was in fact a nuclear reactor when it was 1 minute old.
And 380,000 years later, bits of particles began to cluster, creating the seeds from which stars and galaxies would later form.
Bigger lumps grow to form yet bigger lumps, and so gravity is slowly pulling force, bringing objects together.
What scientists now realize was that at the moment of the Big Bang, dark matter was created. And it played a critical role in helping ordinary matter clump together to form stars and planets. Like steel girders used on a building site, dark matter's slow-moving particles acted like scaffolding upon which ordinary matter could attach itself.
We believe that because it's cold and doesn't interact very much, that dark matter was pulled together by gravity very slowly over time and actually formed the seeds around which normal matter coalesced into galaxies.
It's like a cosmic web, like a spider's web, where there are strands of dark matter, and where these strands intersect, like a scaffolding pattern. So in a sense, the dark matter is the framework. It's providing the scaffolding for the shining galaxies that we can easily see.
Are really like the Christmas tree lights. They're not the actual Christmas tree. They're the things that are visible from very, very far away. But the reality of a galaxy is a big halo, most of which you don't see. You see the shiny bits that are stars and planets that have accumulated at the center of that large halo, which is mostly dark matter.
Scientists have long wondered why galaxies formed in seemingly random patterns across space. Now scientists know it's because of dark matter's gravitational pull.
The universe is not uniform at all, but has voids, it has clumps, it seems to have bubble-like regions. What we now believe is due to dark matter.
In the last year, astronomers have been able to take their theory one step further and create a detailed 3D map of dark matter in the universe using gravitational lensing.
And Einstein said that gravity affects everything, just like gravity is caused by everything. So one of the things that is affected by gravity is light itself.
Because when light goes through dark matter, it bends, just the way light bends when it goes through glass.
And light doesn't discriminate between ordinary matter and dark. Both types of matter batter light's path as it travels through galaxies. Like plotting a course on a map, astronomers have traced thousands of light sources as they pass through dark matter. It has given science the most accurate picture yet of where dark matter hides in space.
We can compare that map of the dark matter with where the galaxies are. And lo and behold, we find that the dark matter is acting as the skeleton. It is the backbone around which the visible material is clumping.
By mapping the universe, astronomers can also look back in time and predict how much matter was created at the Big Bang.
So if you know how lumpy the universe appears now, and when it was half its current size, and when it was half its current size before that, you can infer the total amount of stuff in the universe. It gives us another very nice way of matching onto what we believe is the total amount of dark matter.
It's estimated dark matter makes up 23% of the universe, while ordinary matter makes up only 4%.
You need a lot of dark matter to account for the total amount of gravity that exists in these clusters and galaxies.
But what makes up the final 73% of the universe? Scientists were shocked to discover a new mysterious dark energy was dominating space. And its repulsive energy is driving the galaxies apart. Science always assumed that although the universe continues to grow in size, it would eventually slow in its expansion, or perhaps even collapse on itself. Gravity would overcome any momentum it had. But while measuring the expansion history of the universe, scientists were shocked to realize that the universe wasn't slowing down, it was speeding up. And a grim fate awaited any living thing.
The universe will disintegrate, and temperatures will become so cold that any intelligent life will freeze to death.
From the moment the Big Bang created the universe, space has been expanding and never stopping, carrying galaxies along for the ride.
The space in between the galaxies is expanding, but galaxies are not expanding. The Earth is not expanding, the solar system is not expanding.
Edwin Hubble first discovered galaxies were moving away from the Milky Way in 1929 by realizing the more distant galaxies move faster away from us than the nearby ones. He realized he could measure their velocities by studying their wavelengths through a prism. It's called measuring the redshift and is still used to measure distances in space.
And he found that, in fact, the greater the distance of a galaxy right now, the greater the speed with which it's moving away from us. That is, the greater its redshift.
A few years ago, astronomers decided to use redshift measurements to measure the expansion history of the universe. But how do you measure the entire expansion history of the universe? How do you travel back 12 billion years in time?
We have the capability of going back in time directly to observe the past. So much in the same way as a geologist, looks at layers in the Grand Canyon, and as he goes down into lower and lower layers, looking back in history.
If you look at progressively more distant galaxies, you're looking at them as they were at progressively greater times in the past.
To measure expansion history, scientists used Type 1a supernovas as their standard candle.
One example of a standard candle might be a 100-watt light bulb. You could have a bunch of these things sitting around in your room at different distances from you. Then the more distant ones will appear fainter, and the more nearby ones will appear brighter.
Type 1a supernovas are always consistently brilliant, no matter where they occur in space.
A supernova is the colossal explosion of a star at the end of its life. It just goes kabam! And it occurs when a dying star known as a white dwarf goes through a nuclear runaway and just literally blows itself to smithereens. We find the Type 1a supernovae in very distant galaxies, so they look really faint, and then we compare them with Type 1a supernovae in nearby galaxies whose distances were measured using Cepheid variables or some other technique.
Using these Type 1a supernovas, two different teams set out in the 1990s to measure the deceleration rate of the universe. But to capture supernovas as they occur, astronomers had to put the universe on surveillance.
You can compare this a little bit to perhaps surveying a casino. So all these cameras are on all the time, and most of the time they don't find much of anything interesting, but occasionally they find what they're looking for. You have to look at lots of galaxies. So what we did is we took large telescopes with cameras that have wide fields of view, about as wide as, say, the width of the full moon. And we took many snapshots of space using this wide field camera. And each snapshot contains tens of thousands of galaxies. And by comparing the apparent brightness of the distant Type 1As with those of the nearby Type 1As in nearby galaxies, we can get the distance of the distant galaxies and hence the amount of time that we're looking back in the history of the universe.
After the two teams studied the results of 60 Type 1A supernovas, scientists were shocked at their results. The universe wasn't slowing down, its expansion was speeding up.
We all expected that expansion to be slowing down with time, because after all of the galaxies are pulling on one another.
We were so confident we were going to measure the rate at which the universe was slowing down, and then we found, of course, a negative answer. The universe is not slowing down, it's speeding up, and this was just a big mystery.
That is really, really weird. You know, we expected to measure some amount of slowdown, and instead it's expanding more quickly. That's like the wrong sign, right? We were really afraid that we had gotten completely the wrong answer. We rechecked our measurements, we checked the analysis. A bunch of people on each of the two teams did the measurements and the analysis independently and kept getting the same result.
One of the greatest shocks in the world of cosmology just in the last few years has been the realization that our universe is accelerating.
This repulsive force driving the universe was called dark energy, an invisible energy that was nothing anyone expected or understood.
It suggests that over the largest distances in the universe, there's a repulsive effect that dominates over gravity.
And dark energy was creating space, taking galaxies along for the ride.
This energy that appears to fill the universe and stretch the expansion of the universe faster and faster with time is now known as dark energy. So here I throw the apple, and initially it's decelerating, and then dark energy makes it accelerate away from me. So you throw the apple, and it just zooms away faster and faster with time.
Like the apple forever traveling into space, galaxies are being carried away as more space is created.
So if you could imagine, you know, a classroom populated by chairs, and those chairs are slowly getting further apart from one another within a classroom. Because if all the chairs are being stretched apart, like in the expanding universe, no matter which chair you sit on, you will find all chairs are moving away from you. So the chairs are not really expanding. In fact, the chairs are the same size, really. What's happening is that the room is getting bigger. The space in between the chairs is being stretched apart.
More space is being created in between the galaxies. So you have individual galaxies remaining of constant size in a universe where all of space is getting bigger and bigger.
Dark energy is very different from dark matter.
It doesn't clump up like galaxies do in clusters or like stars do in galaxies. Instead, it appears to be pretty uniform, and we find the same amount of acceleration no matter which direction we look at.
It's probably smooth, although some people believe there may be structure in its distribution and its influence.
Dark energy is the energy of the vacuum, the energy of nothing. Even nothingness has energy, and it's pushing the galaxies apart, creating a runaway universe.
It appears dark energy and dark matter have been at war with one another since the beginning of time. Science believes dark energy was created along with dark matter at the moment of the Big Bang. It has always existed in the universe, but gravitational forces of dark matter kept it in check, slowing down the expansion of space during the first 9 billion years of time. This changed 5 billion years ago when the universe grew big enough so that dark matter was dispersed throughout the universe, and dark energy wasn't so affected by dark matter's pull. As a result, the universe began to expand at an accelerated rate.
Dark energy is a constant term. That was probably very insignificant when the universe was hot and dense in the beginning. And so it doesn't really matter whether dark energy is there or not. It is there, but it just plays no role at all. And then as the universe gets cooler and less dense and bigger, so gravity becomes less important, and then dark energy takes over. It's a property of space that we don't yet fully understand.
As the universe expanded, astronomers realized dark energy won its struggle with dark matter and started the acceleration 5 billion years ago.
So there came a time, about 5 billion years ago, when the dark energy started dominating over the attractive matter in the universe. So in a sense, if you plot the force versus time, the gravitational attraction is declining with time, the repulsion is increasing with time, and about 5 billion years ago, the two curves crossed, and that's when the universe started accelerating in its expansion.
Dark energy is fundamental to understand because it tells us where the universe is going. What's the fate of the universe? Is it going to expand forever and get cold and dark? Or is there, some end in sight?
Dark energy now drives the expansion of the universe, and it doesn't seem to be stopping.
The repulsive effect of the dark energy increased because the more space there is between galaxies, the greater is the cumulative effect of the dark energy, the repulsive effect.
And individual galaxies seem destined to a lonely existence.
So it looks as if this is the end of everything.
Surprisingly, the theory of dark energy was proposed and discarded long ago from one of physics' greatest minds. He called it his biggest blunder. His name was Einstein, and he might have been onto the greatest discovery of the 21st century 80 years before anyone had a clue. Science now understands that dark energy is creating and expanding space. But in the early 20th century, astronomers believed the universe was only as big as the Milky Way and would never grow in size. But Einstein had just formed his theory of relativity and decided to test it on the static universe. But as hard as Einstein tried, he could not balance his equation to equal a static universe. His calculations showed a universe that must either expand or contract.
He realized that if you had a universe that was smooth, that was uniformly distributed with stuff, his theory unambiguously predicted that it should either be expanding or contracting.
So Einstein proposed a repulsive vacuum energy that would hold the universe in balance with attractive gravity. He called it his cosmological constant, a constant energy that would hold the universe in balance.
He introduced the cosmological constant, or dark energy, to hold the universe static.
When Hubble announced space was expanding, suddenly Einstein's cosmological constant seemed irrelevant, and he labeled it his biggest blunder.
Now it turns out that dark energy, the concept that he threw away back in the 1920s, is in fact the dominant force blowing the universe apart. Einstein's so-called blunder will eventually determine whether or not the universe dies in fire or ice. And the betting is the universe will die in ice.
In trying to survey how the universe behaves, Einstein had erroneously predicted dark energy and what is the total makeup of the universe.
The total amount of stuff in ordinary matter and dark matter is not enough to account for the curvature of space that we observe.
Like looking across a horizon on Earth, the size of the universe is so great the curvature of space appears flat.
Add ordinary matter, and dark energy together. That makes a prediction for the curvature of space, and that prediction comes spot on. You get the right answer.
Our satellite data now has revealed the fact that 73% of the matter energy content of the universe is dark energy. Dark energy, which was once Einstein's blunder, is now known to be the dominant force in the universe.
His blunders are our great discoveries.
Scientists are at the very beginning of understanding what effect dark energy will have on the fate of the universe.
Ideally, we'd like to measure how dark energy is behaving as the universe ages.
Eventually, when the dark energy completely dominates over dark matter, the universe will enter a stage known as exponential expansion. For every given unit of time, it'll double in size. And unless the dark energy changes sign someday and becomes gravitationally attractive, the fate of the universe is to expand forever, more and more quickly with time.
We don't understand, if the vacuum energy is driving the acceleration of the universe, why it has the amount it does. That is one of the deepest puzzles remaining in theoretical physics today.
Trillions of years from now, it's going to be a very lonely place. We'll look up in the sky, and the skies will be practically dark. The oceans will freeze over, and it looks as if this is the death of all intelligent life. It looks as if dark energy and the laws of physics are a death warrant to all intelligent life in the universe.
In discovering dark matter and dark energy, science is one step closer to defining the theory of everything. One equation that will define the entire workings of the universe.
Once we have the theory of everything, we'll be able to answer some of the deepest questions ever since man and women first looked at the heavens. This could be the crowning achievement of 2,000 years of investigation into the laws of nature ever since the Greeks asked the question, what are things made of?
For now, dark matter and dark energy continue to be the greatest cosmological questions of the 21st century.
It's certainly frustrating, yes. I mean, it's humbling, too, to know that, all we know about physics is restricted to normal matter, and yet there's all this other dark matter and dark energy that we really understand very little about.
It's the beginning of a new era and the mysteries of the dark side of the universe.
It's the Wild West as far as particle astrophysics, which is what we call this field.
It's a property of space that we don't yet fully understand.
They are cosmic killers.
They're the end of stars. They're the deaths of stars.
Spectacular stellar detonations.
100 billion times as bright as the sun.
That for an instant outshine a whole galaxy.
The most massive energetic event in the universe since the Big Bang.
Out of this exceptional cosmic catastrophe comes creation. But if one struck near here, life on Earth would cease. The universe, the cosmic crime scene for a most violent and mysterious force. Supernovas. Supernovas, the sensational and exceptional death of stars, produce the biggest blasts in the universe.
Now, only a small minority of stars actually explode, but those that do just go kablam, blowing themselves to smithereens.
Releasing more energy than the sun does in its entire lifetime by more than 1 billion.
The spectacular detonation blasts vast amounts of lethal radiation into the universe.
If a star at the center of the planetary system would go supernova and explode, it would probably wipe out all forms of life in that planetary system. Radiation would basically sterilize all forms of life on any planet in a planetary system.
Like homicide detectives poring over clues to a cosmic crime, scientists use state-of-the-art tools, telescopes, and technology to find supernovas and to solve the mystery of how and why they occur.
It's an interesting thing because the explosion, the event, has already taken place. And then we get these clues which we gather with our telescopes and try to figure out what happened.
As the stellar investigators know, supernovas have a dual personality. They have absolute power to destroy. And at the same time, they are fundamental to creation itself.
When a supernova goes off, the explosion produces a lot of light, but it also produces heavy elements out of the light ones. So, for example, iron or calcium or sodium or any of the elements of the periodic table, those things came from exploding stars that went off before the sun was formed.
The elements produced in these enormous stellar explosions actually make planets, plants, and people.
The calcium in your bones and the oxygen that you breathe were all cooked up in stars and blown out into space. The shock waves from exploding stars can compress nearby clouds of gas and trigger their gravitational collapse so that they begin the renewed process of formation of new stars, planets, and ultimately life.
Thanks to circumstantial cosmic evidence collected, experts estimate that a mighty supernova goes off somewhere in the universe once every single second.
So that's something like 30 million per year, and that's been going on for the last 10 billion years or so of the universe's existence.
Giving us a sense of how big the universe is, in a typical galaxy like our Milky Way, a supernova suddenly occurs only once or twice a century. However, nobody knows when the next one might come.
It's a completely random process, so we have no idea when the next one will occur. It could be tomorrow, could be 5 minutes ago, could be another 100 years. We don't know.
If it is very close, you would see a very bright event in the sky. It could be even brighter than the Venus or the planets or even the moon or maybe even the sun if it's bright enough.
If a supernova is too close to you, it can definitely destroy life. The flash disrupts the atmosphere, burns things up.
Astronomers are constantly policing the skies, keeping a wary eye on at least 2 stars in the Milky Way that have the potential to catastrophically explode close to Earth. One that threatens to blow lies in the heart of the Eta Carina Nebula, about 9,000 light-years away.
Eta Carina is one that we know about, which is a very massive star, maybe even 100 times the mass of the sun, has a very short life, and it could be that the end of that life will take place sometime very soon.
Another star in danger of going supernova is Betelgeuse, a star in the Orion constellation. This seething star is 15 times the size of the sun. This one is even closer than Eta Carina to Earth.
It's roughly 500 light years away. It'll be a spectacularly brilliant sight, visible even in the daytime.
There's no question Betelgeuse is going to blow up. It could be tonight, for all our ignorance. It could be 10,000 years from now, short on an astronomical time scale. But it could be tonight that we're sufficiently ignorant about it. So it is worth looking at every night to see whether it's blown up.
Not only do the massive supernova explosions create and destroy stars, planets, and people, they also unleash powerful energy in the form of cosmic rays. These highly energetic charged particles strike our planet each and every day. What's more, they have the capacity to alter evolution.
We live in what I call a disturbed galactic ecology. It is a very eruptive, energetic galaxy out there, and our planet is going to get pummeled by that stuff.
Experts say they can and do change life as we know it.
Well, we know that there are genetic mutations that take place when cosmic rays hit living things. It disrupts the DNA inside cells. And if there were a supernova nearby, there could be a lot more cosmic rays, like 100 or 1,000 or 1,000,000 times more than we ordinarily get. If you're the old species, it might lead to your demise, but it also might lead to new species being developed. So a supernova could be an agent of change, and it could be for better or for worse.
Knowing that supernovas have the power to create and alter life makes it imperative that humankind unravel the riddle of what makes these stellar time bombs tick.
What have you got here?
All right, so this is the supernova factory supernova.
The key to unlocking the mystery lies in the detailed analysis of what is ejected into the cosmos by a supernova.
I'm glad this one did not escape our attention because it was a winner. Yeah. It's a great supernova.
Nature has given us this puzzle. It says, well, I make these objects easily, and we as theorists have to figure out how nature does it.
11825, code 6, 105 North Avenue.
As with any crime scene, critical clues are contained in what is left behind. Like a gunshot, hot gases and explosive debris are propelled through space by these deadly stellar explosions.
Just as these gunshots are driving a shockwave, and you can hear this strong noise from the shockwave, it's actually compressing the matter and heating it up. Shockwave in a supernova is doing the same thing.
As these pieces of shrapnel are hurtling very fast through space, they collide with the material around it, and what forms is a shockwave.
The fantastic stellar detonation shoots vast amounts of ballistic supernova evidence, cosmic debris called remnants, into the universe.
So the remnants are produced as the shockwave keeps on moving out through the universe. It actually produces this very picturesque image of the shock moving outward.
The gases that made up that star are ejected at tremendous velocities, 10,000 miles a second, and so they create an expanding shell, and eventually that can become very, very large.
These things go for thousands of years or even tens of thousands of years. So sometimes we can see the site of a supernova explosion tens of thousands of years after the event has taken place.
The high-speed collision of stellar debris in the shockwave produces intense heat and light in wavelengths invisible to the human eye. They include radio, infrared all the way to X-rays, and gamma rays. Fortunately for astronomers, sophisticated space-based instruments like Hubble, Spitzer, and the Chandra X-ray telescope can help the cosmic detectives see them all.
So basically every instrument in every way you can gives you a somewhat different perspective on what's going on. And then you try to put all that together as an intellectual enterprise.
Like a fingerprint, each supernova has a unique pattern, and they can be analyzed in several different ways.
One thing we can do is measure how bright the supernova is, and that's what we call the light curve. The other thing that we can measure that is really helpful is what we call the spectrum. We take the light from a supernova at a telescope, spread it out into a little rainbow using a prism or a grating, and then measure how much light there is at each color or wavelength.
Analysis of that line can tell us lots of interesting things, like the chemical composition of the supernova, the temperature, the pressures and densities of the gases, how quickly they're expanding, and so on.
Information gleaned from the light curve and spectrum reveals distinctions between each supernova.
So it is much like a detective job where you get different clues from the light curve or from the spectrum and try to figure out what kind of star it was, what made it explode, what the products of the explosion were, and what the effects of that explosion might be.
As time goes on, we can see deeper and deeper into what the star originally was, so we can actually get what the composition of the star was at the time it exploded.
By comparing the light curves and spectra from literally hundreds of supernova cases, scientists have been able to classify supernovas into two main types. Type 1a supernova release no hydrogen. The explosions are uniform in size and luminosity. Type 2 supernova release large amounts of hydrogen. The explosions vary greatly in size and luminosity. But why would there be such distinct types of exploding stars? Might they be blowing themselves apart in different ways? Scientists focused their efforts on uncovering the mammoth question: what drives these stellar monsters to destroy themselves? Like bounty hunters looking for bandits, today's astronomers scour the cosmos looking for deadly supernovas. With their keen eyes on the sky, they belong to a long lineage of stellar observers. In fact, the first supernova ever witnessed by man occurred in China in 185 AD, 2,000 years ago.
The Chinese astronomers kept very meticulous records about what they saw in the sky. Specifically, when something new appeared, they recorded how bright it was, where it was, how long it was there.
Using the Royal Chinese records, stellar investigators today have recently found the remnant of this ancient supernova. It is identified as RCW 86 and is in the constellation Centaurus, near two bright stars known as Alpha and Beta Centauri. 1,400 years after the Chinese discovery, the first European observer witnessed a supernova. On November 11, 1572, 26-year-old Danish astronomer Tycho Brahe was taking a walk when he witnessed a shocking stellar phenomenon in the northern sky. It was right next to the W etched by the brightest stars in the constellation Cassiopeia.
Even though he saw it, and even though he was the leading astronomer of his age, he did not believe the sense of his own eyes.
A few years after Tycho's remarkable sighting, his former pupil, Johannes Kepler, made his own groundbreaking observation of a new star.
He measured from star to star around it the distance, and we can use that now to recreate exactly the position of where it exploded.
When contemporary investigators took a closer look at Kepler's 1604 remnant, they found something very strange about it. A detailed analysis of the chemical composition of the ejected and expanding gases indicated that there were two stars that somehow conjoined to produce a gigantic explosion. So how did this companion cause the stellar catastrophe?
Many stars are in binary systems, so they have a partner that is orbiting around them. And we think what happens is that one star puts mass onto the other.
Experts have since found that the companion or binary scenario is the hallmark of what is called a Type 1a supernova.
The Type 1 supernovae, we think, are the explosion of white dwarfs. So a star like the Sun will produce a little dense nugget about the size of the Earth.
When a star like the Sun dies, it ejects its outer layers and leaves behind just a small, dense, burnt-out core called a white dwarf.
The ashes of the Sun will be a carbon and oxygen white dwarf. Left to its own devices, that will just last forever and cool off.
But when a star has a companion, like a partner in crime, it can lead to catastrophe.
One star puts mass onto that white dwarf, pushes its mass up to the point where it becomes unstable, and that there is burning that takes place in the center. And very, very rapidly, the star goes from being a kind of boring white dwarf to being a tremendously violent and brilliant supernova.
But why do some white dwarfs catastrophically explode? That was figured out in 1930 by a brilliant young astrophysicist, Subrahmanyan Chandrasekhar, the Sherlock Holmes of astrophysics, on a boat trip from India to England.
During this long voyage, he used the newly developed fields of quantum physics and special relativity to come up with the idea that a white dwarf can have only a certain maximum limiting mass. You cannot go beyond a certain mass, about 40% bigger than that of our sun, 1.4 solar masses. And this came to be known as the Chandrasekhar limit. And at that point, an uncontrolled runaway chain of nuclear reactions ensues.
But for decades, scientific investigators remained puzzled by just how this explosive chain reaction worked and what it looked like when it did. Computer models could never recreate what seemed to be happening in nature. But then in 2006, astrophysicists from the University of Chicago's prestigious Flash Center literally cracked the code. The Chicago team was the first to create a supercomputer program capable of processing the vast amounts of data. It had to be to simulate the complicated dynamics involved in the explosion of a whole star.
We call this extreme computing. The computers we use, some of them have 128,000 processors, so they're really 128,000 desktop computers all linked together.
Even with all that power, it took almost 60,000 hours of computing time. The astrophysicists decided not to start their simulated explosion exactly at the center of the star.
The reason that we decided to start slightly off-center rather than right at the center is that it's just very, very improbable that the flame will ignite exactly or even really close to the center. There's just no volume there. There's no there.
According to the remarkable simulation, in 1 second, a flame bubble forms inside the star.
So what you see right in the center of the star is the bubble rising quickly, growing, expanding as the burning takes place, and breaking through the surface of the star.
The molten bubble initially measures approximately 10 miles across and rises more than 1,200 miles to the surface of the star.
It's spreading over the star at about 3,000 miles a second, and it collides at the opposite point on the surface of the star and produces extremely energetic jets. One that's moving outward at about 40,000 miles a second, another jet that's punching in towards the star, and that ignites a detonation wave, which you've just seen race through the star.
Torrid temperatures, depicted using a standard color scale, reach an unfathomable 3 billion degrees Fahrenheit.
And you can see the moment it's just detonated, and going through the star takes less than half a second. The whole burning phase takes less than 3 seconds.
Expert analysis reveals that each Type 1a supernova is remarkably similar in size and brilliance.
This explosion is equivalent to completely detonating a mass the size of the sun.
This groundbreaking computer simulation illustrates for the first time how the explosions could occur in a Type 1a supernova. But Type 2s seem to be a radically different animal. By examining the stellar debris, scientists have reasoned that Type 2 supernovas are not the result of exploding white dwarfs, but rather the huge blasts of massive dying stars, at least 10 times the mass of the sun. But how do these mega explosions work? The answer to the cosmic conundrum would come in the middle of the 20th century. That's when supernova gumshoes, for the first time in history, pounded the intergalactic pavements, systematically seeking gigantic exploding stars. Like detectives on a stakeout, cosmic investigators constantly scan the night sky. They're looking for the telltale bright lights, that are evidence of a supernova. To carry out their surveillance, they use an impressive array of high-tech telescopes scattered across the globe.
Historically, we discover supernovae with ground-based telescopes, either scanning the sky constantly to look for new supernova explosions.
The cosmic supernova hunt began in the 1930s. Maverick astrophysicist Fritz Zwicky led the charge. He was the first to methodically search, catalog, and quantify new and exploding stars.
He was one of the real pioneers in finding exploding stars. And then he wanted to physically understand what they are.
The trailblazing astrophysicist proposed that these enormous and spectacular stellar events were the result of whole stars exploding.
Zwicky predicted that a certain kind of exploding star can occur when a massive star's core collapses and then rebounds, creating a colossal explosion. During the collapse, they said, a compact remnant should be formed, a ball of neutrons, a neutron star.
Essentially, the ordinary matter is made out of protons and neutrons and electrons. In this collapse of an iron core, the protons and the electrons that make up the iron atoms combine to make neutrons.
A neutron star is an incredibly dense object. Now, if you were to take a large building like the Empire State Building in New York and compress it to the density of a neutron star, it would be about the size of a marble.
They have a very high density. And in fact, a teaspoon of neutron star material would weigh as much as 1 billion tons on Earth.
Scientists today believe that only huge stars, at least 10 times the mass of the Sun, have the potential to generate this core collapse type explosion.
The massive star generates energy by fusing hydrogen to helium. It can fuse helium into carbon and oxygen, and it keeps on going all the way up to make iron. Iron is the most tightly bound nucleus. So when a star has made iron, it's really at the end of the line, and it's ready for disaster.
The iron core forms in the last day of the star's life.
And then it becomes so massive that essentially it collapses under its own weight. It just collapses gravitationally very quickly.
It takes less than a second for the core of the star to crunch down from something about the size of the Earth to a neutron star, which is maybe 10 or 15 miles across.
But this dense iron core doesn't settle down peacefully into its new life as a neutron star.
But instead of reaching an equilibrium configuration right away, the neutron star rebounds off of itself, just as the gymnast rebounds off of the trampoline and goes upward again. Well, this rebounding neutron star collides with the material surrounding it and imparts some of its energy to that colliding material, thus initiating an ejection.
However, unlike a gymnast for whom gravity ultimately prevails, pulling him back to Earth, in a core collapse scenario, something else continues to drive the ejection outward. The question became, what was this mysterious force driving the blast into space? Experts calculated that in order for a successful explosion to occur, one more ingredient was needed. They suspected something called neutrinos, ghostly energy-bearing particles that had been predicted but never observed. Astrophysicists believe that during a core collapse, when the electrons are pushed so close to protons in the nuclei of atoms that they combine to become neutrons, in the process, they release these tiny, mysterious neutrino particles.
The neutrinos are kind of interesting particles. They don't have any electric charge, so they don't interact with light. They only interact by what physicists call the weak force. And the weak force is aptly named. It means that these particles can go right through the Earth. They can go through long chunks of matter. So they're like ghosts. They just go through things.
For centuries, modern astronomers had been studying the remnants of supernovas in faraway galaxies from the distant past. But in 1987, they would get a front row seat to an explosion of their very own.
It was the brightest supernova seen in nearly 4 centuries, long after the development of the telescope, so we could use our full arsenal of equipment to study this fantastic blast.
In 1987, the most fantastic stellar event near our galaxy since the invention of the telescope occurred. The first to witness it was young Chilean astronomer Oscar Duhalde. His and astronomy's good fortune came on the night of February 23, 1987.
A telescope operator at the Las Campanas observatories, Oscar Duhalde, put water on for coffee and went outside to take a look at the sky. And when Oscar went out there, he looked at the Large Magellanic Cloud, which he knows very well, and he noticed that there was an extra star.
So he discovered this supernova explosion while basically running outside the telescope building and saw it with his own eyes.
When a star explodes, astrophysicists, like investigators looking for clues to a crime, know that the first few hours after the stellar death are the most critical. So in 1987, when the closest supernova in nearly 400 years appeared, they knew they had to act fast.
It was only about 170,000 light years away, a mere stone's throw for an astronomer. Supernova 1987A was in a small galaxy called the Large Magellanic Cloud, a dwarf galaxy that orbits around our much bigger Milky Way galaxy.
Being the first supernova of that year, the exceptional and nearby exploding star was simply labeled SN 1987A. But this time, dozens of seasoned astronomers all over the planet were ready for action. Armed with sophisticated tools and telescopes, they turned their minds and machines to the heavens and closely scrutinized supernova 1987A. Knowing that an exploding star is at its hottest in the first few hours and is emitting lots of light in ultraviolet wavelengths, the astral detectives sprung into action.
At the time of the explosion, we saw the fastest moving stuff was coming toward us at 1/10 of the speed of light. So that was the actual star blowing up.
Scientists had their explosion. Now they wanted to know the name of the victim. They dug through a catalog that lists all known stars and their positions in the sky when they struck pay dirt. They found the star that exploded. It was tagged SK69202. They also determined that it was a huge star, 20 times the mass of the Sun. Examining the spectral evidence, scientists could see strong lines of hydrogen. SN 1987A bore the hallmarks of a Type II core collapse supernova. But to confirm their suspicions and prove the core collapse theories, experts had to have one more piece of physical evidence. They needed neutrinos, those ghostly particles that scientists predicted would be unleashed during the blast. In the early 1980s, scientists had built a handful of neutrino detectors around the world. They consisted of tanks deep underground filled with tons of pure water. But these detectors had yet to capture a single supernova neutrino.
We've had this story for a long time that most of the energy of a supernova explosion, a core collapse supernova explosion, goes into neutrinos, but we'd never seen those neutrinos.
As luck would have it, on February 23, 1987, they got their neutrinos. 2 detectors, one beneath the city of Kamika, Japan, and the other under Lake Erie in Ohio, captured a dozen of the elusive particles.
There were light detectors on this volume of water that were used to see this little flash caused by the neutrino interacting with matter inside the tank.
For the first time ever, scientists on Earth saw tangible evidence of the mysterious neutrino particles generated in the core of an exploding star. Astronomers now knew the theories first proposed in the 1930s were right.
Supernova 1987A showed beyond a shadow of a doubt that the massive iron core of a very massive star collapsed and formed a neutron star, because in that process a lot of neutrinos should be emitted.
With the deployment of powerful space-based telescopes, astronomers today have built on the astonishing discoveries made in the wake of supernova 1987A. In 2006, 30-year-old astronomer Robert Quimby would once again turn conventional thinking on its head and revolutionize the way astronomers searched for supernovas.
Most supernova searches, they just want to find as many supernovas as possible, so they'll look once every 2 weeks, every 1 week, just so you can find them and so you can look at as many fields as possible and get as many supernovae as possible. So I decided to look at a limited number of fields and look at them as often as I can.
The enterprising cosmic gumshoe programmed his robotic telescope to systematically sweep the targeted field every night. Like an interstellar searchlight, it honed in on and methodically scanned the same small dark corner of the cosmos, looking for supernova suspects.
I had software that can very quickly process the data and tell me if there's anything there that wasn't there before. And when that happens, if I think it could be a supernova, I'll get a spectrum of it. And then that spectrum of it will tell me exactly what it is. Is it a supernova? What type is it? Etc.
On September 18, 2006, Quimby got his big break. He found the brightest supernova ever.
And this is my 4th supernova. I didn't think that I should be so lucky. And others looked at the spectra and they started taking their own measurements of the photometry, how bright it was. And they figured out that, in fact, 2006 GY was brighter than any other published supernova.
Very slowly. Took over 2 months, 70 days to get the maximum light and then faded again. So it was a supernova unlike anything we'd ever seen before, discovered by this 4th-year graduate student at the University of Texas.
Analysis of the remnant indicated that the star, before it exploded, was 100 times the size of the sun. And with lots of hydrogen showing in its spectrum, the brightest supernova ever recorded bore the stamp of a Type II event. Then Quimby topped himself. When he finally analyzed a seemingly insignificant supernova he found earlier, called SN 2005AP, he made a stunning discovery.
It was something like 100 billion times as bright as the sun. As compared to, for a Type 1a supernova, the peak may be only 6 billion times as bright as the sun.
It was even brighter than SN 2006 GY. Like circumstantial evidence, astonishing discoveries of new ultra-bright supernovas like 2005 AP and others have opened up a whole new avenue of inquiry into exploding stars and their MO.
The basic idea we have is that perhaps this is connected somehow to gamma ray bursts.
Gamma rays are the most powerful form of light known in the universe. By analyzing supernovas, investigators are getting closer than ever to solving some of the most confounding riddles in the cosmos.
How one of them makes gamma rays and the other makes an ordinary supernova is still one of the big mysteries. Nobody really knows how that works.
What astronomers do know is that supernovas and the gamma ray bursts associated with them are the brightest beacons in the universe. On the galactic highway that is the cosmos, supernovas serve as celestial signposts, pointing astronomers to the beginning and the end of time and space. NASA's powerful SWIFT satellite, launched in 2004, was designed specifically to sweep the sky and detect gamma ray bursts in the universe. Like cosmic first responders, astrophysicists at NASA's Goddard Space Flight Center in Baltimore, Maryland, are standing by 24/7, waiting for a 911 call from SWIFT.
Basically, less than 2 minutes after SWIFT discovered a gamma ray burst, the satellite sends down emails directly to our blackberries.
When a recent supernova, recorded as SN 2006AJ, appeared, the SWIFT satellite caught the shocking gamma rays it generated.
And that gamma ray burst was very interesting because, first of all, it was a very long-duration gamma ray burst. Usually gamma ray bursts are very short-lived phenomena, only fractions of a second or a few seconds. But this gamma ray burst was visible for like 35 minutes. We saw 3 days later a supernova explosion going off at the exact same location. And this solved one of the important mysteries of gamma ray bursts, because we found out that at least parts of gamma ray bursts are due to massive stars that are exploding.
Astronomers today can see hundreds of supernovas and the deadly gamma ray bursts they generate. On the cosmic highway, scientists use these stellar headlights to ascertain the bounds and breadth of the universe.
You can use supernova to probe the universe, because if they're very dim, you know they were very far away, and then you can study the curvature of space-time and all of the cosmology that you can study with them.
For example, if you're on a desert highway and you're looking out at the lights of the cars, you can tell which are nearby and which are far away from the apparent brightness of the lights. The ones that are nearby look bright, the ones that are far away look dim.
Measuring how far away things are very systematically will tell you about the size, the age, the shape, the history, the future of the universe.
It turns out that Type 1a supernovas are the best suited for this purpose.
One of the things that's really interesting about the Type 1a supernovae, the ones that are exploding white dwarfs, is that there is this fixed mass, this Chandrasekhar mass, that sets how big the explosion is, how much stuff is involved. And the consequence of that is that many of these have very nearly the same brightness. If the explosion produces the same amount of light, then we can measure how much light we see and figure out how far away the supernova is.
This is known as the standard candle principle.
Type 1a supernovae are like standard candles. They all have about the same peak power, the same peak luminosity. So if you look at them from different distances, they appear different apparent brightnesses. They look dimmer if they're farther away and brighter if they're more nearby. So if we find Type 1a supernovae in distant galaxies and measure their apparent brightness and compare that with the known power of a nearby Type 1a supernova, we can determine the distance of that supernova and hence of the galaxy in which it's located.
The trailblazing technique has also led astro-investigators to some radical conclusions.
Basically, you can use the distances to supernovae to figure out what the universe is doing, how old it is, and we now know that from various lines of evidence that it's a little less than 14 billion years old. But in particular, found out that the universe was accelerating when we thought it was decelerating in the grip of the gravitational materials in it. That's just caused an intellectual revolution, like throwing a ball up towards the ceiling, and rather than having it come back down into your hand, it goes faster and faster and faster towards the ceiling is completely counterintuitive.
Basically, all the astronomy textbooks out there all said that the universe should be decelerating. That is, gravity should be slowing down the expansion rate. But what this result showed is that instead of slowing down, it was actually expanding faster and faster and faster.
While the examination of supernovas has helped scientists unravel many monumental cosmic mysteries, experts believe that if they continue to follow the clues left behind when huge stars explode, they'll be able to answer the biggest unanswered questions. Today, scientists know that someday soon we could each witness for ourselves the marvelous and almighty force of a supernova.
Our galaxy is 100,000 light years across, so that means there's light from 1,000 supernovae that's on its way to us now.
It could even happen in our very own Milky Way.
In our galaxy, we are expected to have on average about 2 supernova explosions per century. The problem is that the last supernova that we saw in our galaxy is almost 400 years ago. So our galaxy is long overdue.
If it did happen in our own galaxy, we, like the titans of space and time, Tycho, Kepler, Chandrasekhar, and Zwicky, would bear witness to the most destructive and the most creative force in the universe, the supernova.